The topic of my presentation is physics-informed feature-to-feature learning for design space dimensionality reduction in shape optimization. A typical simulation-driven optimization starts with a CAD model created in a CAD tool whose parameterization creates a design space which is explored with optimizers. The optimizer searches a design instance which is updated through the shape modification method. The performance of the design is then evaluated with the time-expensive solvers which guides the optimization towards global optima. However, these pipelines suffer from the high computational cost, which is mainly associated with the dimensionality of the design space. As dimensionality increases, the computational cost of the components of this pipeline increases exponentially. Previously, this computational burden is tackled in different ways. For instance, some researchers proposed unsupervised feature extraction techniques which extract the latent features of the design space to create a lower dimensional representation of the original design space. Moreover, recently, the supervised learning techniques have also gained tremendous attention to bypass the need of design evaluation with computationally demanding simulation codes such as FAE and CFD. A typical process to build such model starts with the sampling of the design space, which along with their physics creates a training dataset. This dataset is then fed to the supervised learning techniques to construct the surrogate model. For complex engineering design problems with high dimensionality requires large training dataset. The construction of such datasets again causes the whole process to suffer from computational complexities as it requires running numerous physical simulations. To tackle this problem, these methods often benefit from feature extraction techniques in which a lower dimensional design space is first created and the surrogate model is constructed on this subspace. As the subspace has lower dimensionality than the original design space, therefore it would require a relatively less number of training samples. However, these subspaces only retains the geometric variability of the designs and no information about the design's physics is incorporated. Therefore, such construction can result in low prediction accuracy of the surrogate models. Therefore, our objective is to propose a two-step feature extraction pipeline in which we not only extract the geometric features but also the features are based on the physics, which are then augmented to create a lower dimensional latent space. Once constructed, this subspace not only contains geometric variability of the design in the original design space but also the functional variability. Afterwards, this subspace is exploited for surrogate modeling and optimization to obtain an optimum design. Consider a geometric domain representing a design. In our case, it is a shape hull and a shape modification function which for any given input creates a new design. This parameterization creates a high-dimensional design space which is represented here as a hypercube. Here we want to extract features of this design space which retain maximum geometric variability to create a geometrically active subspace. This extraction of the features starts with the construction of a coherence matrix whose eigen decomposition gives eigenvector and eigenvalues. The eigenvalues represents the variance resolved and eigenvectors forms the basis of the new space. After partition of the eigenvector based on eigenvalues, we get a set of active and inactive features. Here we are only interested in the active features as they retain maximum geometric variability. The linear combination of these features with original design variables creates a variable for geometrically active subspace. Once this subspace is extracted, the next step is to extract the functional features of this subspace which retains maximum variability. The extraction of functional features follow a similar process. In this case, the covariance matrix composed of the gradients of the functions f with respect to the geometrically active variable. The eigen decomposition of this matrix follows the partition, gives the features along which the function changes the most. The linear combination of these features gives functionally active variables which act as coordinates of the new functionally active subspace. This subspace contains both functional and geometric variability. Once this subspace is constructed, it can be used for efficient surrogate modeling and design optimization. To validate the proposed method, we used a widely used naval ship model, and the objective for optimization is to minimize the wave resistance coefficient. This design creates a 27-dimensional design space in which 900 designs were sampled for learning functionally active subspace. The performance of these designs was evaluated using wave resistance program developed at CNR Encina. From these results, it can be seen that conventional single-step method creates a 5-dimensional subspace. The proposed steps provides a 4-dimensional design space. Even though there is no significant difference between the two approaches in terms of dimensionality, however, we will see in the subsequent slides that the surrogate model trained in the subspace extracted from the proposed approach has higher accuracy. In our method, we use Gaussian process regression to build the surrogate model. The Gaussian regression is a non-parametric and Bayesian approach. During training, the hyperparameters are optimized using the following equation, and squared exponential function was used as it provided the higher accuracy. It can be seen that the mean square error for the model trained with two-step extraction is lower than the one obtained with single-step method. Furthermore, the wave resistance coefficient obtained from this subspace is also lower. Let's conclude that the two-step feature extraction provides better results in terms of reduced dimensionality, higher accuracy of the surrogate model, and quality of the final optimal design.